Combustion of the air-fuel mixture in the cylinders generates heat which produces high pressure to force the piston down in the power stroke. Not all of this heat can be converted into useful work on the piston, and it must be removed to prevent seizure of moving parts. This is the role of the cooling system. Most engines are liquid-cooled. A liquid-cooled system uses coolant, a fluid that contains special chemicals mixed with water. Coolant flows through passages in the engine and through a radiator. The radiator accepts hot coolant from the engine and lowers its temperature. Air flowing around and through the radiator takes heat from the coolant. The lower temperature coolant is returned to the engine through a pump. Air cooling is common on smaller internal combustion engines. Some engines use cooling fins. Their design makes the exposed surface area as large as possible, which allows more heat energy to radiate away and be carried off in convection currents in the air. Some engines also use a fan to direct air over the fins. Air cooling is common on many smaller internal combustion engines, especially outdoor power equipment and most motorcycles. Air-cooled engines are also used in larger vehicle applications of up to 100 horsepower or 75 kilowatts. Even some small aircraft engines, up to approximately 160 horsepower or 120 kilowatts, use air-cooled engines. The air-cooled system is designed for use in extreme conditions and where weight is important. These engines still generate a lot of heat which must be dissipated to prevent seizure of the engine caused by the overheating of the components. The air-cooled system is usually simple in design and works best on an engine that's exposed to a high airflow. This can be achieved by direct exposure to the outside air or by high-volume forced airflow over the engine via fans, ducts and cowlings. Most air-cooled engines use cooling fins, making the exposed surface area as large as possible, which allows more heat energy to radiate away and be carried off in convection currents in the air. The more air that flows over the fins, the more heat is carried away. This means that when a vehicle is moving at speed, airflow over the engine is high, but at low speeds or during idling, heat builds up. A common way to maintain adequate airflow over the engine is to use a fan with shrouds and ducts to direct air over the cooling fins. This helps maintain a cooler engine temperature in low-speed driving or while idling. A fan can be driven by an electric motor, or it can be driven mechanically, usually by a fan belt attached to the crankshaft.
In this very basic liquid cooling system, a coolant is stored in a radiator and in the engine. As the engine heats up, a natural circulation starts, as coolant rises through the engine block by convection. It passes through the top hose and into the radiator. Inside the radiator, heat is removed from the coolant as it falls from the top to the bottom. When it reaches the bottom, it returns to the engine through the lower radiator hose. This process is called thermosiphon. It was common in older cars which had low-powered engines and high, narrow radiators. In modern cars, the engines are more powerful and radiators are low and wide, and a thermosiphon process couldn't move the coolant quickly enough. Instead, a water pump forces it through passages called water jackets in the engine block. It collects heat and becomes hot itself. Heated coolant then returns to the radiator for cooling. And the cycle is repeated. Heat is removed from the engine and dispersed. Preventing overheating is one function of the cooling system. It also helps the engine reach its best operating temperature as soon as possible. Every engine has a temperature at which it operates best. Below this temperature, ignition and combustion can be difficult. Most engine wear occurs during this warm-up period, and most pollution too. One function of the thermostat is to shorten the warming up period. It operates according to coolant temperature. When coolant is cold, it is closed. When a cold engine starts, coolant circulates within the engine block and cylinder head and through a coolant bypass to the water pump inlet. It can't get to the radiator. As the engine warms up, the coolant trapped in the engine gets hotter and hotter. This starts to open the thermostat, allowing hot coolant to flow to the radiator.
In a rotary engine, the rotors are cooled by oil from the lubricating system. Each housing, however, is water-cooled, and there are additives in the coolant to protect the housing alloys from corrosion. The water pump takes coolant from a bottom radiator tank and pushes it through water jackets in the housings towards the rear of the engine. The chamber is surrounded by coolant passages. Inside the housing is hollow, and it forms a water jacket. A pulley on the end of the eccentric shaft drives the water pump and fan. In the rear housing, the coolant reverses direction and returns to the front of the engine. It passes a thermostat. As in a piston engine, it is closed when the engine is cold, but opens as it warms up. The rotary engine has an overflow system much like that of a piston engine. As pressure builds up, coolant expands into an overflow tank. As it cools, pressure drops and it returns to the radiator. A viscous hub links fan speed with engine temperature. The internal combustion engine works by changing heat energy into kinetic energy. There are many ways to do this, some better than others. But no matter how efficiently it is done, and no matter the size of the engine, the heat energy generated never completely changes into kinetic energy. Some energy is always lost. This is certainly true in internal combustion engines, where only about a third of the heat generated is transformed into the mechanical energy that moves the piston and turns the crankshaft. Another third goes out the exhaust, wasted. The rest tries to spread round the engine. Heat always moves from areas of higher temperature to areas of lower temperature, which can be a problem. To control this movement, it is necessary to understand how heat is transferred. Heat travels in just three ways. The way it moves through solids is called conduction. Through liquids and gases, it is called convection. It follows paths called convection currents. Through space, it moves by radiation.
Coolant prevents an engine from overheating in use and from freezing when idle. The amount of heat generated by an engine is the equivalent of that required to heat a large house in winter in very cold climates. As engines and vehicles become smaller and more powerful, they generate even more heat in a confined space, and aerodynamically efficient body designs tend to direct air away from rather than into the engine bay. When an engine stands idle in cold weather, water in the cooling system will expand as it freezes, and this can have sufficient force to crack the engine block or radiator. An effective coolant must therefore contain good heat transfer properties, have a higher boiling point and lower freezing point than water, prevent corrosion and erosion, resist foaming, be compatible with cooling system component materials, be compatible with hard water, resist sedimentation, and be as chemically stable as possible. A concentrate, usually made of ethylene glycol together with some protective additives, is mixed with water to produce coolant. Propylene glycol, which is non-toxic, is sometimes used in the mixture as well as, or even instead of, the more toxic ethylene glycol. Glycol does not absorb heat as effectively as water, but when added to water it has the ability to lower the fluid's freezing point as well as raise its boiling point. A common glycol-to-water ratio used is 50-50. This will lower the freezing point of the fluid to minus 39 degrees Celsius, minus 38 degrees Fahrenheit, or 70 degrees below freezing, and raise the boiling point to 108 degrees Celsius, 226 degrees Fahrenheit. Manufacturers can recommend other specific mixture ratios, but below 33% glycol the coolant will give inadequate freeze protection, and above 65% glycol the mixture has inadequate heat absorption. There are three types of additives used in coolants: conventional or inorganic additives, organic additives, and a hybrid mix of the two. A fully formulated coolant is comprised of a careful balance of ethylene or propylene glycol with rust inhibitors, corrosion inhibitors, scale inhibitors, pH buffers for the acid-to-alkali balance, anti-foaming agents, and reserve alkalinity additives. Coolant should be changed at recommended intervals because some of the additives will age and deteriorate over time, reducing the effectiveness of the coolant. While some coolants are compatible with others, changing the chemical balance in the cooling system can affect coolant performance, so mixing different types of coolant is not recommended. This water is open to the atmosphere, or at atmospheric pressure. It is heated, and it boils. The thermometer shows its boiling point. Now the water is put under pressure, higher than atmospheric pressure. It's heated and it boils at a higher boiling point. The pressure is decreased. The water again is boiled. But at what temperature? Compare these boiling points. Raising pressure above atmospheric pressure increases the boiling point. Lowering it below atmospheric pressure lowers the boiling point. So changing water pressure can change the temperature at which it boils.
Many radiators are mounted at the front of the vehicle in the path of greatest airflow. The air carries heat away, cooling the liquid before it returns to absorb more heat from the engine. Where a radiator is mounted also depends on space, how the engine is mounted. A header tank can be mounted away from the radiator where it provides a coolant supply, stored above the engine. It can be made of sheet metal or hardened plastic. The radiator has two tanks and a core. The materials used in the radiator must be good heat conductors like brass or copper. Brass and copper are often used for tanks, combined with a copper core. Modern vehicles often use plastic tanks, combined with an aluminum core. This saves weight, but still provides good heat transfer. The core consists of a number of tubes that carry coolant between the two tanks. The tubes can be in a vertical downflow pattern or a horizontal crossflow pattern. A crossflow radiator fits more easily under a steeply sloped hood. In the core, small thin cooling fins are in contact with the tubes. The shape of the fins increases the surface area exposed to the air. Where coolant touches tube walls and where the tubes touch the fins, heat is removed from the coolant by conduction, then by radiation and convection at the surface of the fins. Air rushing by carries the heat away. Liquid emerges cooler at the bottom of the radiator. It travels through the lower radiator hose to the water pump inlet, then through the engine again. Coolant is transferred throughout the cooling system by hoses. Most vehicles have the engine mounted on flexible mountings to reduce noise and vibration. Since the radiator is mounted to the vehicle body, flexible hoses are needed. Coolant is also carried to the heating system, which is usually inside the cabin of the vehicle. Coolant hoses vary in diameter, depending on the volume of coolant that passes through them. Heater hoses carry a smaller volume. Most hoses are made of rubber, and since they are subject to pressure, they are reinforced with a layer of fabric. They are molded to a special shape to suit the model and make of vehicle. Some heater coolant hoses also have special shapes. All hoses are subject to hot coolant and high under-hood temperatures, and they can deteriorate and fail. The water pump is usually in front of the cylinder block, belt-driven from a pulley on the front of the crankshaft. A hose connects it to the bottom of the radiator where the cooler liquid emerges. It has fan-like blades on a rotor or impeller. Coolant enters the center of the pump. The rotor spins and centrifugal force moves the liquid outward. It is driven through the outlet into the cooling passages called water jackets. Water jackets are passages in the engine block and cylinder head that surround the cylinders, valves, and ports. Coolant can be also directed to hot spots, such as the exhaust ports in the cylinder head, to stop local overheating. Finally, hot coolant is ready to leave the engine. The thermostat helps an engine to warm up. It's found in different positions on different engines. It is a valve that operates according to coolant temperature. When coolant is cold, a spring holds the valve closed. When a cold engine starts, coolant circulates within the engine block and cylinder head, and through a coolant bypass to the water pump inlet. It can't get to the radiator. As the engine warms up, the coolant in the engine gets hotter and hotter. This thermostat has a wax-like substance that expands as the engine nears its operating temperature. This starts to open the valve. Coolant starts to flow to the radiator. Thermostats have a small hole or valve to let out air that was trapped in the engine block. Heated coolant is pumped from an outlet in the cylinder head. It goes into the upper radiator hose, then to the radiator. In a vehicle moving at high speed, airflow through the radiator cools the coolant. But at low speed, or when the engine is idling, extra airflow comes from a fan. Fans can be driven in different ways. More and more modern vehicles now use an electric fan. Air-conditioned cars often have extra fans. Electric fans can be behind the radiator, in front, or both. This arrangement would be difficult with a belt-driven fan. Some fans can be driven from the crankshaft. When an engine is mounted longitudinally, its fan is usually mounted on the water pump shaft. The drive belt then turns the water pump and fan. Some use a hydraulic link from the power steering system. Fan blades can be rigid or flexible. Rigid blades tend to be noisy and use more energy. This noise can be reduced by using irregular spacing of the fan blades. Some vehicles use a shroud to direct all of the air that the fan moves through the radiator core. At high speeds, plenty of air is already flowing through the radiator. If the fan is always working at full speed, it's a waste of energy. And since the engine drives the fan, it's a waste of fuel too. What's needed is some way to control the fan. A heat-sensitive switch in contact with the coolant can work like a thermostat and turn the fan on and off according to coolant temperature. Another way to alter the speed of the fan is with a viscous hub. This type of fan slips when it's cold, but as the engine heats up, it grips more and more. Overheating can seriously damage an engine, so having warning of trouble is obviously useful. A device that's sensitive to engine temperature sends readings to a temperature gauge or a warning lamp. To give an accurate reading, this sensor must always be immersed in liquid. Indicators that measure coolant levels can give warning if the level falls too low.
If a coolant boils, it can be as serious for an engine as having it freeze. Boiling coolant in the water jacket becomes a vapour. No liquid is left in contact with the cylinder walls or head. Heat transfer by conduction stops, heat builds up, and that can cause serious damage. One way to prevent this is with a radiator pressure cap that uses pressure to change the temperature at which water boils. As coolant temperature rises, the coolant expands, and pressure in the radiator rises. It soon rises above atmospheric pressure, and that lifts the boiling point of the water. Engine temperature keeps rising, and the coolant expands further. Pressure builds against a spring-loaded valve in the radiator cap until at a preset pressure the valve opens. In a recovery system, the hot coolant flows out into an overflow container. As the engine cools, coolant contracts and pressure in the radiator drops. Atmospheric pressure in the overflow container then opens a second valve, a vacuum vent valve, and overflow coolant flows back into the radiator. And that stops atmospheric pressure collapsing the radiator hoses.
A recovery system maintains coolant in the system at all times. As engine temperature rises, coolant expands. Pressure builds against a valve in the radiator cap until, at a preset pressure, the valve opens. Hot coolant flows out into an overflow container. As the engine cools, coolant contracts and pressure in the radiator drops. Atmospheric pressure in the overflow container opens a second valve, and overflow coolant flows back into the radiator. No coolant is lost, and excess air is kept out of the system. Like water, air contains oxygen which reacts with metals to form corrosion.
To refill coolant, begin by carefully removing the radiator pressure cap. This will allow air into the system, which is necessary for the coolant to drain quickly and completely. Next, find the drain plug or valve for the cooling system. It's located on the bottom of the radiator tank. Then place a clean drain pan underneath. Be sure that the pan is large enough to hold all the coolant. Once that's finished, open the drain plug and the coolant will drain into the pan below. When all the coolant has drained out, close the plug. Check the vehicle specifications to find out how much coolant the system can hold, and for the recommended type and mixture of coolant for the vehicle. Using a funnel, pour the recommended amount of coolant in through the top of the radiator. Next, leave the radiator cap off and run the engine for a few minutes. The coolant will circulate and get rid of any trapped air. Then replace the radiator cap and run the engine at high idle to bring it up to operating temperature. Return to the coolant reservoir and check the coolant level. Top it up to the high or hot engine mark. Finally, remember that antifreeze is toxic, so dispose of the waste coolant carefully and in an environmentally recommended way. Electrolysis is a chemical and an electrical process that takes place when electrical current passes through a liquid, such as water, causing molecules, such as hydrogen and oxygen, to separate. In a cooling system, electrolysis can remove the protective layer inside a radiator tube, and because it results in the buildup of static electricity, It can also cause serious engine failure. To check for electrolysis in a cooling system, find a voltmeter that can measure DC voltage. Next, set the meter to DC, and then place the positive lead into the coolant, and attach the negative lead to a good ground, like the frame. Once that's finished, record the readings. A voltage reading of 0 to 0.3 is normal for a cast iron block. The reading for aluminum engines should be half that amount. Any reading above the normal range indicates a problem. Before adding coolant to a system, you should check the freeze point of the coolant already in the system. And for that, you'll need a refractometer. It's a tool that uses light to determine the freeze point. To use a refractometer, begin by taking a coolant sample from the system and place it on the surface of the prism. Next, close the cover plate and press down. Then look through the eyepiece. The corresponding dial boundary between light and dark will give you the freeze point of the coolant.